Welcome to second 3M Embedded Firmware Talks. Today we will discuss AMD IOMMU in more details. So let's look at the agenda. I will not reintroduce myself. You can find my LinkedIn and Twitter account in internet. So what we will talk today, we will recap what was last time. Then we will talk about the details of AMD IOMMU, which will cover some features, IoTLB. Then we will discuss more about features, about some extended stuff. We will switch to how it operates, what's the theory of operation, and what's the suggestion for implementation. Then we will discuss ACPI tables, which are required for which are required for correct operation in operating system. Then we will discuss more about state of the implementation in coreboot, how it started, who did the main work, and what's going on right now. And finally, we will go how it was tested. So we have quite a lot of material to cover, so let's move on. Okay, so first of all, last time we discussed what DMA is, what MMU is, what IOMMU is, how it is related with virtualization. So in short, IOMMU is just the MMU for IO devices. DMA attacks are problematic because if there is no MMU control or IOMMU for devices, then devices may access random memory, and accessing this random memory may compromise some of our sensitive data like passwords and private keys and so on and so on. We discussed some basic features of IOMMU, so that we talked about translation, about interrupt remapping, and some other neat features that typical IOMMU provide. And we also discussed some IOMMU commercial implementation, which is AMD VI and VTD for Intel. Okay, so this is typical system for which includes AMD IOMMU. So what we can see here, we have like CPU. Of course, this is mostly in one SoC package, like this part, CPU plus memory controller, the hypertransport link, the IO hubs, and IOMMU this is in the same. Of course, DRAM and IO devices are like external stuff. So what we have in our SoC, for example, in PCNG's platform, is CPU that has some memory controller which is connected to DRAMs. This memory controller is also connected to like a sold bridge, we can say, which handles all the I/O communication. So we have like LPC here, SATA, PCI, probably USB, PCI Express, and all that stuff. So hypertransport is a connection between IOMMU and memory controller. IOMMU contains something which is called translation look-aside buffer, or we will call it IO translation look-aside buffer. We will talk about that later. This is very important for conversion of the device virtual addresses to physical memory addresses. Of course, there may be some integrated peripherals in the sold bridge. This is kind of general configuration. In our system, in PCNGs, we have just one IOMMU. So, but in theory, there may be more. So this is just an example for you to have in mind. It is important to remember that we have hypertransport here. Okay, so basic features that are always supported in all IOMMU, AMD IOMMU implementations are things like device virtual to physical address translation, interrupt remapping, and access permission checks. So these are always enabled things. Other things can be enabled through registered caller EFR sub, which resolves to extended features register support, we can say. So this register is quite big. It's 64-bit. Of course, we have various neat things here. I will not go through all details because this is like 200 pages of spec. So what's interesting is that we have quite a lot of reserved stuff, which AMD don't want to tell us about. And yeah, so that's mostly all. This came from AMD IOMMU spec. Okay, so I told you about the TLB, and there is something called IoTLB. So IoTLB is a TLB for IO devices, which is in IOMMU. And TLB typically is just a cache, like a hardware-supported cache, which contain entries that help us in converting virtual addresses that our operating system see to physical addresses that are reachable in memory, in physical memory. So we can look at this picture. This is like came from Wikipedia. It's like simplified view of what TLB is. And in TLB we distinguish two situations. When CPU requests some logical address or virtual address, then it may face a situation where it finds this address in TLB. So this is the TLB hit, which is here, yeah. Or it may be a situation when we miss, so there is no translation to physical address. So this situation is quite good because we have performance improvement. We found translation and we know what we want to access, and we can immediately access physical memory, get this data and return to anyone who requested that. But when we have a miss in TLB, then we have to go through the page tables, and I don't know how much familiar you are with page tables structures and all those complex things related to memory management. But we have page directories with page directory entries. Then these entries lead us to page tables. Then page tables got their entries, and this is quite big structure. And this cause going through this structure just simply takes time. And when we're doing this a lot, and typically with application we're doing it a lot, we have performance drop because of this looking for this memory. Okay, so that's the problem of this situation. And of course this cache wants to improve the situation, and IoTLB is just a cache for our IO devices. When those devices request some device virtual address, we check IoTLB. If this address is, we know what it translates to, and if it's not, then we have to get through this page table walk and find this address. Okay, so of course TLB is infamously known from Spectre meltdown problems, like because this can be used. The timing of hits and miss can be used to leak some information, but this is different topic. Okay, so how it looks in practice? In practice, we can use, for example, x86 info application and just look at the what kind of TLBs we have, how many entries there are already there, and so on and so on. So there are applications for that. But looking inside the TLB is kind of not easy thing and requires, for example, additional kernel module which can help with that. Okay, so what about the extended features? So AMD IOMMU spec mentions 28 software visible features. I cannot distinguish all of them. It's hard to me to understand all of the nitty-gritty names. But as I said, so we have this base support things. So we have IO page tables which can be translated. We have interrupt remapping. We have so other features are enabled through capability header, and this capability header has two things, can enable disable our huge 64-bit register with various things, or can enable disable our IoTLB support. So which may cause performance drops if we disable that. Okay, so yeah, so that's all. So the most interesting features that, from my opinion, are SMI filter. So we have something like system management interrupts, and those interrupts were infamously used for many attacks. So we may want to protect ourselves and intercept all SMIs that are unexpected. And this is neat feature. I didn't try that, but it would be interesting to, for example, if we have real-time sensitive application and don't want to have any interrupts, any SMIs. The question is if we can block all the SMIs. Yeah. So this would be something that if researched can provide very interesting output. Next we have something which is called guest page table and XBit, and access protection. So this is like in normal MMU. So page tables have pages have NX bit, and NX bit just say if this page contain executable code or not executable code, and if this page contain supervisor or kernel code, or this page contains some user code. So there are typical things like which we have in MMU. So this is typical protection, and we can disable that for our guest operating system in virtualization environment. And there is something called memory address routing and control. So this is something because we talked last time that IOMMU may cause performance drops, and we may want for some devices, for some regions of memory, to not have this conversion from device virtual address to physical address, and that's why we have this feature which we can say, okay, this range will not be translated and it would be directly accessible, despite that IOMMU is enabled and configured for other devices. Okay, so how the basic operation look like? So if we have IOMMU disabled, it simply pass all traffic. You remember this this picture when I showed this architecture. So we have this notion of downstream devices and upstream devices. So downstream devices are on the bottom of the picture and just going to the CPU, sending something, or to memory, yeah, sending something. So in enabled IOMMU, IOMMU intercepts all traffic, so all the reads and write requests, and perform permission checks, translate those device virtual addresses, and then send translated addresses to memory for some operation. And to support this process, IOMMU use 3 tables. One table is permission checks table, address translation table, and interrupt remapping table. And all those tables are cached just to improve performance. And the maybe not so good thing is that software is responsible for invalidating this caching of these tables. So software have to maintain coherency of these tables. Okay. And what's interesting is that IOMMU can detect various events, and then based on this detection we can perform some actions. For example, all the responses, because there is communication, there is like we can say there is a protocol that using which we can communicate with IOMMU and agree on some things. So all these events and all this communication can be logged. We look for IO page faults, which is very important for operating system because it can perform some actions. If, for example, if there is IO page fault because someone accessing memory which is not there, or memory which is which simply this device should not access, yeah. So we can be asserted, and IOMMU can let us know that okay, someone trying to access memory that it should not. And finally, we have memory access errors. For example, if some ECC errors happen, we can be asserted about that. Okay, Implementation consideration. So from the perspective of the firmware developer, we have to know that probably there is no one system that can implement all the 28 software visible features as AMD claim. So there will be always some subset, and we have to realize what kind of subset we want to support. And the recommendation from the specs are as follows. So we as a firmware developers should perform initialization, because if hypervisor or operating system starts, it should face already configured IOMMU. So this is probably to improve performance, improve security, because we cannot rely on some invalid IOMMU configuration facing kernel, because we can significantly change the behavior of the platform. Okay. And I faced that during enabling. I faced that I can crash kernel when I'm doing something wrong with the configuration of ACPI tables which describe the configuration of IOMMU. And firmware should describe IOMMU in ACPI tables. This is preferred method. This is like a UEFI way, we can say. And unfortunately, the same thing is about Intel VTD. Both technology use ACPI tables to expose information on how IOMMU is configured. And those tables, Intel and AMD have different tables, yeah, so they use different tables. So there have to be different drivers and so on and so on. And those tables are not part of the ACPI spec. Those are like a custom ACPI tables for vendors. And firmware must preserve or restore IOMMU configuration between any power management transitions. So if we have S3, firmware have to detect that it was S3. Okay, what was the last configuration? In theory, we should have that in boot script, but in practice, probably there are some problems there. I don't believe it's correctly implemented. And yeah, so that's kind of could be a problem, not restoring that correctly. Of course, the key point is like, okay, we're going to sleep. We have some IOMMU configuration. We have some devices access to some memory, and then we get back from S3, and suddenly, for example, this device have different access to different memory. So that's bad. Yeah, that can cause some problems. Then. Yeah, so I'm not sure about that. I'm discussing with Ulf Risk about if this is true, if we really have to do after PCI enumeration. That's what spec's saying, because we want to, maybe other way. This have to be done, if we want to create ACPI tables, we have to do that after PCI enumeration. But configuration of IOMMU can be done before. And probably is, and probably should, because yeah, according to Ulf, this may be a security problem if we're not doing that. Okay, let's go to the ACPI tables, the fun stuff. Of course, they invented quite a lot of structures. The key one is IO virtualization reporting structure, which describes configuration capabilities and virtualized device in IOMMU. What's important here, this table contains various options that I will basically discuss. I will not go into details because we just, short on time. And these tables contain entries of IO virtualization definition blocks, which we distinguish two types. One is for devices and one is for memory regions. And there is alternative way, which is IO virtualization device tree, and this would be great if someone would implement that in that way, but firmware developers, which are mostly tied to Intel, which is like IBVs like AMI, Phoenix, and so on, those guys using ACPI instead of device tree. Okay, so this is how IVRS looks like. Nothing fancy here. This is signature that can help in detecting that. this part is important, IV info, I will talk about that. And the most important part is here, and we have like numbers of IO virtualization definition blocks following, which, so just to say what it does, it just describes either memory, either IO devices which are connected in the system, and for example, what's interesting if we consider hot plugging some PCI devices. So, okay, so for example, when we have PCI engines, we have these MPCI slots, and let's assume those slots like we can do hot plug, MPCI hot plug with these devices, yeah. So the problem with IVRS is we have to enumerate all possible devices that we plan to hot plug if we want IOMMU support. Yeah, so that's bad thing. But of course, like if IOMMU protect us, if we bought this in China, we don't know what kind of firmware is here, and we don't want to allow, let's say, this MPCI card to access our memory. Yeah, so we just want it to do its stuff and not more. Yeah. Okay, so let's move on. So we have to define all the devices here. Yeah, I will not go through that. I don't think it's important. The important thing is that we may have various versions of those tables that define those devices, and that's kind of problematic because various versions have various capabilities, and then drivers expect various versions of the tables, and so on and so on. This is kind of problematic, and probably not all combinations are implemented in the Windows or Linux systems or Mac. Okay, so I told you that there is IV info in IVRS ICPI table. Not much here. Like mostly we define guest physical addresses, and you know, like what kind of physical address, what kind of virtual address this IVRS or our whole IOMMU can access. So and of course, and there is information if extended features are enabled or disabled. So this is passed through that part. What's important here, like these are configuration for PC engines. So we have like a maximum physical address and maximum virtual address for this platform configured. Yeah, and guest virtual address is also like a maximum defined. Yeah. Okay, so that's it. Yeah, so each IOMMU in system is described by yeah. So there is mistake here. So IOMMU device. Yeah. So each device which is handled by IOMMU have to be described by IVHD block, which is kind of entry inside the IVRS ACPI table. And I will show you the structure in a second. Yeah. Yeah. Maybe like move back. Like IVHD block contain entries, which can be either memory, either devices, and I will show these entries in a second. And we mainly have two types of these entries. Like for devices, we have two types of these entries, which can be fixed length, which are just 16-bit representation of bus device function, or we can have variable length, which then cause like an interpretation of this device and looking for this device through ACPI human interface device names. So this is kind of ACPI way of explaining where in the system this device is. Yeah, because PCI way is bus device function, and this ACPI of course had to invent its own way of looking for the devices. And some devices can be probably found only using ACPI ID. Okay, so this is our IVHD block. So I already, and here we have the entries. Okay, so yeah, so in PC engines we use type 10, type 11 of IVHD is more robust, I would say, more extensive, is bigger, contains some additional features, but you know, it doesn't. I will not go down with that because it's like kind of complex, and I don't feel also I understand all the possible things. So some features are completely related with hypertransport, like what will happen if this kind of message arrive to hypertransport and have those bits set, and what we will do with that. So so it requires, I don't know, to understand that it requires at least quite a lot of knowledge about the hypertransport, PCI Express, and to really to understand that probably good hardware that can intercept and look at the frames, what's going on and how it works. I don't know if this can give any performance boost. Okay, there are second type of the, instead of this device entries, we have memory entries, which just define some memory blocks which are which can have some restrictions. So we can say that, okay, this block cannot be accessed, or we can say, okay, this block is accessed without any problem, without any permissions, and so on. So this kind of information. So what about the implementation? So QubesOS implemented stuff in March 2016, doing like mostly relying on what AGESA binary blob returns. The problem with that is that AGESA values are how to say that, maybe not exactly invalid, but at least causing problems. So those values have some assumptions, and truly I don't believe they are very conscious about how they design those tables and what exactly they expose. I'm pretty sure it will not work on all possible devices and may crash many of them. So those tables just simply invalid. And this is normal stuff. Like when we try to look at the DMAR table, which is IVRS for VTD, if you Google that, you will find like hundreds of people looking for workaround for DMAR or IVRS table to like patch it, to make something with it, because the default version provided by the vendor just does not work. Yeah, and you know, if people use binary blobs from AMI or Phoenix or Insight, they just can't change anything, and they have to use software workarounds, which is not easy. Okay. Other thing was that there was only a single isolation domain, so you can assign all devices or nothing, so which doesn't help, because on PCNGs, what we want to do on PCNGs, like what most requests from customers are things like, okay, let's make this port or this port assigned directly to VM, and let's say this VM is a pfSense firewall, and all traffic just coming here, no touching by the operating system, which handles whole platform. It goes to firewall, and firewalls then internally redirects to VMs what's needed. And let's say like second port is for other VM, and third port is for other VM. So the people mostly want to do that. With one isolation domain, you can assign all or nothing. So not something that people wanted. IVRS patching was just binary patching, which was also the problem, and stability across three bots was problematic. Then Timothy Pearson from Raptor Engineering in June, almost next month, implemented better version, but with like a very nested code, very big code, which just set each byte in the structures, in IVRS structures, and manually created IVHD type 10 structures, I would say, or ICPI tables, entries. Okay, and quite a lot of hard-coded values without explanation what it does. And then so kudos to QubesOS and Timothy, because without them, for sure, we will not be able to move this forward. And like 2 years after, we picked up the patches, and based on that, we tried to do the rebase. We did the rebase. We redesigned the code according to information in review, and we just clearing that up and want to merge it into mainline. So far it was not yet merged because there are still problems with that. And to be testing using Zen 4.8, community testing that with KVM. So there is some coverage here, and I'm using a long-term stable for DOM 0. Okay, so what's the state right now and what's the implementation? Okay, I told you about the broken IVRS. We have random hangs, like 29%. Like we have remote testing environment, which do the automating testing, and we figure out that for 100 boots, we have 29% of failures, and that's bad. And we really don't know at this point why is that. It's somewhere in multi-processor initialization area. So I will debug that, and right now I just created the development environment with help of my friends in 3MDep, and I just trying to speed this up because it's like I'm booting over Pixie. I want to modify Zen kernel and want to see what's going on, and hopefully soon we'll have some results. What kind of code, files in coreboot were modified? So, like mostly Node bridge. So what we did, like this contains new PCI ID. This guy's device tree for PC engines just enable IOMMU in device tree. The binary P, we added driver, which is quite of simplified version of driver. Probably should be extended. And then key changes are here. Because this file defines ACPI IVRS tables and all the entries, and this is key work and key debugging in this area. And of course, there were initial version of AGESA initialization was not exactly correct because it disabled IOMMU and didn't assign the IO APIC, so there were needs also for change there. And also you can see that difference are very, very small. It's like 300 lines of code. Of course, this is like after my redesign, and probably we have to extend that with various features. So how we tested that? We used Zen. We booting Zen over Pixie. We trying to do PCI pass-through. So to do PCI pass-through on Zen, you just have to mode probe Zen PCI back if you don't have compiled that into kernel. Then you assign the device, and the bus2 device 0 function 0 is just middle port in PC engines. And we just redirect that, we assign that to device, and this is the guest is HVM, so this is hardware virtualization. So this is not like a para virtualization or something like that. This is just hardware stuff. And then, oh, it's terrible. Okay, so this picture I wanted to show here that this is inside this guest created by Zen, and you can see that there is a device 0, or can see device 0. Byte 0 device for function 0, which is exactly Intel Corporation i210 gigabit network connection. So this is our network card, which is in PC engines, which I directly connected to guest, and guest see this as a hardware inside. Yeah. So this is how the config look like. The key part is here, and of course we want HVM. And this is config that I used for installation, so normally you don't have this one. And of course, you have to replace IP address. Okay, so Zen 4.8, I told you that. Debian Stretch, Linux, I did that with much more, much recent version. pfSense and testware with iPerf, and you can find details on our blog. Okay, so the tests. Of course, this is also not visible very well, but you can if you look carefully, you can see that there is 941 megabits per second, and this is inside our hardware guest. And this test is outside. This was in our local network, and you can see exactly the same result, like no difference. Yeah? So yeah, so this is great. Yeah? So that means that we have this PCI pass-through working. Yeah? And IOMMU of course have to help in that, because without that there is no way to assign for virtual memory, for virtual guest, assign some kind of hardware and piece of memory that can talk with that hardware. So, and of course interrupt remapping, all that stuff, it's required, because without that there is no way the guest will, you know, treat hardware which is not virtual. Okay, so yeah. In previous talk, I explained you what's DMA attack, and that IOMMU protects against DMA attacks. And so ideally it would be if in this talk I will prove that DMA attacks are not possible on this device. But it happened to be not so trivial, and I'm in discussion with Ulf about with the maintainer of PCI Leech, and we already obtained PCI Screamer. It's in our office and waiting for action, and we will for sure report some information to community how it works and if it really protects. Of course, right now Ulf confirmed, because luckily he also has that APU device from PC Engines. He confirmed that firmware is vulnerable and there is problem there. But of course, you know, you have to have physical access, and if you have physical access, it doesn't make sense. It's like mostly protecting ourselves against supply chain attacks and this kind of stuff, or maybe attacks on GSM modems or Wi-Fi modems, or Wi-Fi cards, because if someone will get to our Wi-Fi MPCI card, then maybe it can attack through DMA, attack the system. Okay. So, and other research around that was done by Google, and Google claims to fuzz Intel VTD in their data center, and they found some bugs, but after fixing those bugs, right now everything is correctly protected, and that's nice, but they didn't reveal any information about that. Yeah, so those things like PCI Screamer is good topic for next talk, I believe. And what's the current state? So as I told you, this is like, I already told you that. We probably should think about the longevity test, because someone just have to run it for like, I don't know, a year and see if nothing's broken. Or maybe at least 6 months. Okay, references, so I mentioned mostly this specification, but this specification, the architecture programmer's manual, also contains some interesting stuff. And may help in understanding the other one. Okay, so let's summarize. So key point from this two-part talk is binary blobs are bad. Why are those bad? Because if you end up with AGESA or FSP providing you incorrect ACPI table, you may just not have features that your hardware provide. And that's the problem. Like, you want to use protection, you want to use like hardware supported virtualization, and you know, your firmware vendor may just don't care about that, and just through firmware limits your ability to use hardware for which you paid. Yeah. And what future work we plan? We're thinking about enabling advanced features of IOMMU. As you saw, like, we have 64-bit extended feature register, so it's not a lot of things to play with. The key point is here, like, how to prove it really works, because some features are just not visible to the software. GPU pass-through, like, I don't know if this is possible on AMD, on PC Engines, since the question is if this is electrically correctly connected and so on and so on and so on. I'm not sure what's the state of GPU, but let's dream for a second and think that GPU pass-through is possible. So then we can, for example, run, let's say, Windows VM with graphics, hardware accelerated graphics somewhere. Yeah? So that would be interesting. Yeah. So like hardware accelerated graphics for remotely accessed Windows. Yeah, that's just dreaming. Yeah. Yeah. So this proving that it's protected, and of course, in part 1, I told you about this dream towards reasonably secure router IoT gateway, and it would be a great first step to have IOMMU protecting our system, and then move on with stuff like secure boot, TPM, PSP, and all the cool stuff. Okay, that's all. Thank you very much, and let's go to the Q&A.